Okay. So I have to thank the organizer for the invitation, and so this conference is dedicated to the memory of Andrei Zelevinsky. And so we were friends for many years with Andrei, but it happened that we wrote just one paper. It was a paper on parameterization of canonical bases, and it was just in between his work with Gelfand and his papers with Arkady Berenstein. And I remember how enthusiastic Andrei was about these results. And for me, it was a little bit uncommon to see such an open, enthusiasm. But I have to tell that Andrei was equally enthusiastic about papers written by somebody else. So in this case, he was actually very generous and open. So I will talk about the non-commutative Laurent phenomenon. And so this is part of our joint work with Arkady Berenstein. And this work is on non-commutative clusters. We try to understand for several years what are non-commutative clusters. But we started actually with discussing Laurent phenomenon because cluster algebra, this is just a very useful, actually very elegant tool to prove different versions of Laurent phenomenon. And I remember sort of a lecture given by Professor Stanley in our university, and he talked about Laurent phenomenon and applications of the paper of Sergei and Andrei. Okay, so let me just maybe recall a few things. So first of all, that suppose I have variables x1, x2, xn, commutative or non-commutative, then a Laurent polynomial is just a polynomial in x's and their inverses. Just it's called the Laurent polynomial. Now the thing is that if you consider just a composition of two polynomials is a polynomial, a composition of a Laurent polynomial and of a polynomial and Laurent polynomial is actually Laurent polynomial. And the problem begins when you try to compose actually two Laurent polynomials. What can you say about this? And a very simple example is, of course, for example, if you have L1 equals, say, x plus y, L2 is, say, z inverse, then if you plug z, if you put z equals x plus y, then you don't know how to inverse it. So the inversion will be a series and not a polynomial. Okay, so when it happens, we talk about Laurent polynomials. So we say, let's say L1, L2, Lk are Laurent polynomials. And we say that the sequence satisfies so the Laurent phenomenon if this composition so if the resulting result is again Laurent polynomial in x1 and xn. Okay, and also another, of course, thing, if you have actually sort of a directed graph. Sorry?
Probably need something more general than individual Laurent polynomials, like maps.
Yeah, so I will tell about this. And suppose if you have also a directed graph, and to say gamma, and to each vertex corresponds, say, a sequence of variables depending on this vertex, and when you have an edge, say, like this, and then you know that x1, each of these guys can be expressed as a Laurent polynomial of this. So of this set, and you say that you have a Laurent phenomenon for this graph, if it's actually for any path in this graph, you have just the composition will give you again a set of Laurent polynomials in this set of variables. Okay, and so there were a lot of results about Laurent phenomenon in a commutative case, and so we tried to do non-commutative case, and actually so we had some examples that I'm going to talk about, but of course a great help was for us, well, sort of confirmed that we are on the right track, was actually a talk by Maxim Kontsevich called Noncommutative Identities. And it appeared in archive in 2001. So he describes some questions about Laurent. 2011, I'm sorry. So it's 2011, yes. Oh, I'm sorry, 2011. 2011, okay. All right. So let me start with one of our main examples. And I will recall again I will start with the commutative case. And in commutative case, so there are algebras defined by what we call Ptolemy, or I would prefer to call it Ptolemy-Plucher relations. And the algebra is described like this. You have a polygon, and I will consider sort of all polygons inscribed somehow into a circle. So I will call sides and diagonals. So I will call them chords. And so the corresponding algebra is generated by Xij, and say Xij and their inverses, and Xij corresponds just to a non-directed chord, and then the relation that you impose are the following. So whenever you have just this so quadrilateral, and so you have just this diagonal. So to this picture corresponds a product xik times xjl equals to xij times xkl plus xil times xjk. So the product of diagonals, roughly speaking, is equal to the sum of product of opposite sides. So there is now, if you have just a triangulation, of Pn, and in this triangulation you have again sort of a picture like this. Then you can flip the diagonal, and so to go from this to this, and so in this flip xjl, for example, suppose well, it's easy for me. Sorry, let me go from this to this. So somehow, and then in this flip, you have xjl equals to the Laurent polynomial in 5 variables.
Your points are not ordered, right? So just the polygon doesn't have initial point, or it does?
I will order later. So here, so the points are ordered in this way.
No, I mean the initial point. Cyclically ordered or ordered?
They are always cyclically ordered.
There is no point number 1.
No, but in my picture it will appear. It will appear in examples. It will appear. Okay, and then the thing is that if you have a triangulation, say you have this 5 gone, and you have a triangulation like this. Well, okay, so let me put numbers I3, 4, 5. And then by flipping one diagonal at a time, you can get, say, this diagonal which go from 2 to 5, and then x to 5 is a Laurent polynomial, can be expressed as a Laurent polynomial in all sides, and so just, well, x1, 2, x2, 3, x5, 1, and then x1, 3, and x1, 4. And this is what's called Laurent phenomenon. Okay, now the thing that you can do this for any triangulation and any polygon comes from the theory of cluster algebras. And in fact, it was the first example that actually Andrei showed me about this thing. But so just later, just a combinatorial expression, exact combinatorial expression of this Laurent polynomial, I believe, was done by Ralph Schiffler. And I will discuss a non-commutative version of the Schiffler. Is this correct? Okay. Now let me just go to non-commutative version. Yes. So yes, all coefficients are positive here. Okay. All right. So maybe I will erase this as well. Now I will talk about non-commutative Ptolemy-Blücher relations. And so first of all, I have to replace, to talk not about unordered hordes, but I need actually ordered hordes. So it's important where the direction go, from I to j or from j to I. Okay, so to any ij corresponds a formal variable xij. Okay, and xj, and to if you go in the opposite direction, it corresponds xji, and they are distinct. In general, they are distinct. But also then, I need also to invert those polynomials, so I will associate also to the polynomial. So let me just do this connection both ways. And then if I will talk I minus 1, say, then it corresponds exactly to also to this direction. So if I invert, I have to invert my hordes. Okay, now suppose I have just this. And I impose, so exactly like this. And so I impose actually two relations here. One is relation is xjl equals to x ik inverse xjk xil plus x ki inverse ji x chi kl. So this relation is replaced by this one. And I need one more relation, so I will write it, and then I will explain how these guys are related. And so this is actually what we call Ptolemy-Blücher relation. So Ptolemy-Blücher relation, but I need an important relations, which we call triangular. And it can be written like this, xij Okay, so let me compare this. So before, let's say that all these monomials, they have actually a geometrical meaning. Again, if you interpret, say, xij as a path from I to j, then basically what you have is the following. So here you have jl, here you have ik. And if you want to go from j to l, you do this sort of in two ways. You go from j to k, then from k to I, and then to L. And this is exactly what this monomial says to you. So you go jk, ki, il. As I said, when you have inverse, you have to make this. And another relations would be that you go from j to I, then from I to k, and from k to L. And this is what this monomial. So any questions?
Yeah,
Yes.
And somehow I'm looking what you wrote. You say that ij arrow has both xji and xji inverse. Is it misprint or?
Where? This one?
To the left. In your conventions.
Here?
Just
This one?
No, that's
below.
This one? This one.
IJ.
Oh, sorry. It must be ij. I'm sorry. I'm sorry. Yes, sure. Oh, thank you. It was.
xji equals xij inverse.
They are not equal. They are represented by the same. They correspond to the same path, but they are not equal. Yeah. Yeah. You know, this is like morphism, like category morphisms, and so. Okay. So this is what this relation means. Now about this one. Well, maybe I have some place here. And this one just means that if I have I, j, k, then I can go from I to j, then from j to k, and then from k to I. But I'm always just flipping what is inside by inverse. So I'm writing with the inverse. So to jk, it's just this arrow corresponds to xkj inverse. And this is just path in the opposite direction. So if you go into this direction, you have this.
Can you tell us what the object is that you are working with it? Like is
Okay.
it a pure field or a wave?
Yes, okay, yes. So I am working actually with the algebra generated by xij's and inverse, and for all directed towards ij. It's an associative. It's an associative. Yes, 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 yes.
And so how do you know that this algebra is non-commutative?
Well, okay,
All right, but for more than you don't know if it's non-commutative.
Okay, but this is actually, those are just my relations. I'm talking about relations here. Now, let me explain how these relations are and commutative relations are connected. Then I will go to motivation, and then I will show you that the algebra with this identity satisfy so the Laurent phenomenon. Okay. Now, if you how to go from this to this, well, just put. If you impose the identity that xij ji, so you forget about directions, then so this identity just corresponds to this one, and this identity is redundant. Yeah, in the commutative case, for this is commutative case.
How can you check that something is not a Laurent phenomenon? There are like infinitely many ways to write it.
Yes, but yes.
No, but if you don't know the algebra,
You know, I am more interested when it is Laurent polynomials, and just I'm writing formulas for this. So that's.
but the point is to prove that something is a Laurent polynomial.
Yeah, okay. All right, so this is just our relations, and now let me explain the motivation for this. And let me first point out why you can consider this relation also as a Plücker relation in the commutative case. And if you have, say, a 2 by n capital C matrix, and if you impose Pij, you say that Pij are just determinants and you said that Xij are just Pij, you have exactly this relation, which is the famous, the celebrated Plücker identity. And this is exactly what we used. We used actually then a non-commutative version of this Plücker identity to get these relations. So now I'm going to describe non-commutative Plücker coordinates. Yes, yes, but no, but all I say that in this case, so this is redundant. So if I impose this relation, then I will get so. Yeah. Yes. 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 This is exactly. Thank you. Okay. So this Plücker relation so gave us a hint. Because now I have to recall what are sort of non-commutative quasi-Plücker relations. Or also non-commutative quasi-Plücker coordinates. So they were introduced by Israel Gelfand and me in 1997. And I will just discuss them only for 2 by n matrices. Well, I have to add that it was actually Andrei's idea that I could be useful for Gelfand team, so sort of. So I have to thank him for this as well. Okay, now I will fix, say, let D will be just a skew field. So non-commutative or non-commutative algebra with division. And I'm considered, so suppose you have just this matrix. And let me define first a notion which is a version of a Schur complement, but which we call quasi-determinant. And I will do this only for quasi-determinant. And this basically means that if I have a matrix like this, say, I will do only 2 by 2 matrix. So suppose I have just a matrix by this. And suppose I will choose an element in this matrix, say this one. Then this expression is equals to 1j 2i inverse a to j. Well, again, you can see that you can compose these if they are morphisms in a category. But, of course, so in the commutative case, you have just a relation up to a sign. You have the relation of determinant divided just by this element. But I can start actually with any element, for example, with the element like this. Say with the element like this, and it means that this 1i inverse 1G. So again, you can always write any of these expressions if you know what is the boxed element, and you use the rule how to compose morphisms in a category. Okay, so now let me just introduce. Well, I'm sorry, I have to erase this, but I will reconstruct these relations later. And so I will introduce now elements parameterized by three indices, I, J, and K. So I will do this like this. Okay, so this is the ratio of two quasi-determinants, and it is equal, and you can prove this, to the ratio of these two guys. So if you box two elements on the same level, you have the same result. Sorry, it's 2I must be here. Okay, I'm sorry, it must be I, of course, here. That's all right. And then J here. Okay, so those guys, they have a common, one column is common here and here. Those are different. And actually, if you, in the commutative case, basically what you have here, you have just a ratio of two. You have a ratio of two Blücher coordinates. Now, the rule is the following, that those guys are GL2 of D invariant. So if you multiply this matrix by GL2 of D, you have the same expression. From the left, it's just, okay, those are called left Blücher coordinates. I can introduce right Blücher coordinates, but I don't need this. And I have actually three relations for these elements. And so one is a trivial, this is just a trivial relation. Another one is this. So you have three indices, and so they all are changed in this way. This product is always equal to -1, and this is what you call noncommutative skew symmetry. And if you will, like in the commutative case, if you will use just this formula in the commutative case, you always have, you will get this -1. So let me maybe skip this. And the Blücher identity looks like this. You have Qij times Qjil plus Ql Qlik equals 1. So what you do, basically, you exchange these two indices. And this is the analog of the Blücher identity. And so let me maybe explain why. This, again, so in the commutative case, I have P, say, well, let's say JK, PIK. And then I have P IL over P J JL plus P LK over PIK times P sorry, must be J, excuse me. There is misprint this one. And I have Pij over PLJ equals 1. And you have that I almost have the common denominator except for signs, but I can exchange this by PIJL and simultaneously this for PKL. And then if I will do this, I have a common denominator. If I will get rid of this common denominator, I have exactly the Plücker identity in the commutative case. Okay, and now then again, I don't want to tell, but geometrically, basically, it means that you add two non-commutative cross ratios and you get one. This is sort of a non-commutative cross ratio, but I don't need this. Okay, now how these formulas motivate our choice for non-commutative Ptolemy-Plücker identities. So again, so that's so let me just recall. So my identities looks like this. And also this. So they look like this. And suppose again, I have a matrix. This is and I assume now that all those guys are free variables, free non-commuting variables, and the skew field generated by all these variables I will denote to F. And I will construct two homomorphisms from this algebra to F, from the algebra generated by all these elements to F. And it goes like this. Xij goes to, well, it must be a sign here. And so I will call this, say, phi1. And another one, so I have to change to check those signs, but the idea is clear. And then one can check that this. So the proposition is, or a theorem, that they both are homomorphisms. Injective homomorphism, thank you. Injective homomorphisms. And Well, I can, but right now, even if this is not important because this is just a motivation. And then this identity will actually impose so that if I have this identity, then I'm getting this relation. And from the main identity, I getting so just this relation. So, and this is why we invented it. Okay? Yes? Why we discovered this. Okay, sorry. All right. All right. And now let me formulate you our first theorem about a non-commutative Laurent phenomenon in this case. And let me do this. So what is an I put a razor somewhere. Okay, doesn't matter. So suppose I have a polynomial. Well, let me just write this maybe for simplicity. So I have a polynomial, I have a polygon Pn with vertices, say, from 1 to n in a cyclic order. Okay. And then I will consider sets, actually, of indices, well, of these indices. So this is just, so I have even numbers. Well, I have even numbers here. So this. And to this set corresponds a monomial that I will write in this way. So this is just a product, and each even term is inverted. And I would say that this set is IJ admissible. And this is just a direct, or maybe not. J is admissible if the following identities are if so. First, so if admissible if, well, you start with I and you end with J. Then, 2, you demand that each chord intersects IJ. There is always an intersection. And 3, that for any pair S which is less than T, so the intersection point for its 2S. is closer to I than the intersection point I to T, well, plus 1, also this. Okay, so that's the condition. Now I will formulate a theorem.
This intersection point is well defined.
Well, this,
You are allowed to go back, right? On steps.
so I will show you just an example. That's, yes. I should probably write maybe on this. So I have to check if this one is. I think one is one. Yes, I think yes. Okay. Okay. So those my intersection points. I can just operate with them.
One step, there is no restriction, right?
No.
You can go back and then you go forward.
No, I cannot go back because of this, I believe. So I cannot go back. Okay.
Back and then you go forward so that the intersection is ahead.
Yes. Okay, so let me just give you an example, and then just it will be clear. And the theorem is actually saying, so let delta be a triangulation of this guy, and I to j, then xij can be expressed as a sum xi over all I which are admissible, ij admissible in this sense. In this sense. Okay. Now, if you then identify, again, if you identify in the commutative case xij, I believe that you can get the formula produced by Schiffler.
You assume that all of the chords are in the triangulation.
Yeah. I have to tell yes, so that all these guys comes from the chords in triangulation. So I have to check. Sorry. In particular, they don't cross each other. All right. Okay. So I don't have time. So I will give you just one example how it works. And so suppose I have just this triangulation, and I want to describe the variable corresponding to this edge. And the example is x25, which is equal x21, x41 inverse, x45 plus x23, x13 inverse, x15 plus x21, x31 inverse, x34, or x14 inverse, x15. So let's discuss. So to this monomial correspond the following paths. I go from 2 to 1, then from 1 to 4, but I have to inverse, and then I'm arriving to 5. For this guy, again, well, that's similar. I go from 2 to 3. Then I'm going from 3 to 1 with inverse, and then I'm arriving to 5. And this is the longest one. And here I go from 2 to 1, then from 2 to 1, then from 1 to 3, I have to invert. Then I go from 3 to 4. Then I go from 4 to 1, and I have to invert, and then I'm arriving in 5. And I have other examples written here, but I don't have time. All right, now since we are dealing with the elementary geometry, let me describe here what are actually non-commutative angles. And to describe what are non-commutative angles, so suppose I have a triangle like this. The second, this. Okay, so suppose I have a triangle like this, and I will, to this angle, corresponds to the following expression, which can be written as xji inverse, xjk, xik inverse. Well, again, categorically, you can multiply those guys. As a morphism, you can multiply those guys. Then the triangle relation says that these guys are sorry? Oh, sorry, it's kj. And the and then the Ptolemy-Pluki relations can be written in the following form: JL equals to TIJK. Here you have L plus TIKL. So TIJK is exactly this angle alpha. This is this angle beta. And what is the rest here? You could call this angle gamma. And so this is an additive function. Now then, for the polygon Pn and any triangulation, if you consider the sum of all such angles, then due to this relation, it does not depend on your triangulation. Yes, in each corner. So if you have, well, here you have to do this each corner. Well, here, so you have to do each corner, and so on. So yes, well, it's true for each particular I. Yes. Okay, yes, you have to fix I, and you have to do this. And so then the sum, again, in the commutative case, you know, so, but, so you do this for each I. In the sum, you have 2 pi n minus 2 in the commutative case. So from here, you can get an idea of what is non-commutative pi in this case. Okay, so this is just okay. But then, okay, I have no time, but let me just waving my hands. And they say that you can generalize this thing for triangulated surfaces with a marked point and punctures. And so this is like, again, many people in this audience did. Well, I can just, well, there are. Well, I'm sorry, I wouldn't name all names. There are several names doing this. And so we can actually do this theory in this case as well. And in particular, not only just do the theory, but get some useful corollaries. For example, by using this and by applying this to a certain, by applying this theory to a cylinder with one point marked here and several points marked here, we are getting so the solution of a conjecture by Kontsevich, published in this talk that I raised, and the Kontsevich wrote the following recursion in these variables. And this is when n is even. And this is when n is odd. And the condition is that k is greater than 3 and k is odd. So Kontsevich wrote this recursion. So you can use this to define u sub n as a Laurent polynomial in the rest of the variables. And so he conjectured that this recurrence satisfies to the Laurent phenomenon. And from this geometric theory, we were able to prove it. Okay, and since I have like 2 minutes, maybe let me also mention that it's interesting to study the triangle relations only. So for surfaces, again with the marked points and punctures. And so you have a group. And so we were able to compute this group in several cases, including spheres, and so spheres with punctures. And when you do these groups, you have sort of a fundamental group for something, and it looks like a fundamental group for ramified two-fold coverings, but this is what experts told us, and actually this is part of our, so we are going to address this. And I have no time for other phenomena, but so let me just stop here. Thank you. Yes.
So in the commutative case, this path formula also provided a way to compute the principal coefficients for each path. Do you have a
No. I believe that the advantage in the non-commutative case, and that's always this, that this is rigid. So basically, you know what to multiply. So I guess that probably what you have in mind is that in the commutative case, several non-commutative terms maybe can be equal, and from that should be it. But yeah, so it was used. But again, let me just repeat that the advantage of non-commutative case is that it is rigid, and basically that I know what I can multiply and what I cannot. For example, I know that I cannot multiply x1, 2 and x3, 4. That's forbidden. I can only multiply x1, 2 and x2, 3, which is not in our case. And I can then only multiply things like this, basically. But again, that's, yes?
I believe for arbitrary surfaces, Brown and Craig used Theorem Laurent.
Yes.
Williams have a formula, expansion formula for these Laurent points, right?
Yeah, yes.
Do we have a non-commutative?
Yes, like this. So we have actually, so the formula that I wrote for polygons, we can generalize this. Yes. Yes. But again, well, I'm sorry, I saved my time, and I didn't mention names, but definitely that's Laurentness over there. So those are our plans, and so hopefully when we will develop enough so the general theory, we will be able to do this. But so right now we stick with this case. But again, this theory of non-commutative Plucher coordinates exists for all Grassmannians. Yes. Yes.
So in all your computations, each term appears always with coefficient 1, right?
Yes. Yes, and in this case, I forgot to tell that also that all coefficients here are positive, actually, or +1. Yes.
So if you're in the surface case of wave functions, are the formulas similar to?
Yeah, similar. Yeah, they're similar. Yes. Yes. Okay.
Yeah, so I asked before about non-commutativity. So apparently this homomorphisms imply that this algebra is non-commutative, right? Because
The,
you map to a non-commutative algebra, and it is clear that the image is non-commutative.
yes.
But you said that you also can show that this map is injective. So how do you, if you don't give, I mean, I presume it is hard to construct some kind of basis of this algebra. So
Yes. Well, there are some tricks to do this. So, but so let me just. Maybe I can sit.
So do you know the size of this algebra?
Yeah.
And another question was, you call this non-commutative angle, but so as far as I understand, in the commutative case, these ij are lengths of the chord.
Right.
So why is it an angle then? It doesn't.
Okay. I call it a triangular angle, and this is angle in quotes, and I can take my terminology back. Let me just say that all I have, that you have an additive invariant, or that you have functions with which you can add. So I would not fight for the terminology. But yes, it depends. Okay. Well, so Sasha is saying that this is sort of a potential. Well, okay, that's a more intelligent word, definitely. Yes.
All right. Thanks, Vladimir, again.
Thank you.